Okay, so next up we're with Lucy. Lucy's a software engineer who works at SEiT in gaming. She studied biomedical sciences at university, but discovered a passion for software engineering. She enjoys the constant challenge of learning new technologies and building automation. In Lucy's talk, she's going to be talking about how the technology field is really diversifying. So engineers come from various backgrounds and may lack some foundational knowledge. It provides an overview of core software engineering principles that are often assumed. Over to Lucy. She's open to questions at the end if we have time. Otherwise, please grab her at lunch.
Cool. So yeah, hi everyone. I'm Lucy Llewellyn, and yeah, we're going to be looking at going back to basics and looking at some fundamentals of software engineering that, if you can code, people might assume that you know. So yeah, my journey into tech. Not going to lie, at GCSE time when I was forced to take a GCSE in ICT, I thought computers were super duper boring, and I think that's mainly because GCSE ICT at the time was basically just using Microsoft Word. Very, very dull. So didn't consider doing anything to do with computers in the future. So I went to university and did biomedical science. And I thought when I went there, I might end up being some sort of genetic scientist or something, because I really liked DNA. And then in my second year, I did an optional module where I learned some Python, and I was instantly hooked. Didn't realise coding could be so fun. And I was, I'd say, semi-good at it. So I thought maybe a career in tech could be for me. And then fast forward to graduation, ended up being accepted onto the Tech Academy grad scheme at SEiT in gaming, where I'm currently still an SEiT. So that's kind of how I got into tech. So why am I doing this talk? People that come into tech doing a technical degree like computer science, you tend to learn quite a lot of foundational knowledge that can really help you make your code better. And those of us that don't do that degree, we don't end up with this knowledge. And also when it comes to tech, there is so much jargon. People will say all these fancy words to you and assume you know what they mean, and it's just gibberish to those of us that have no idea. But 9 times out of 10, I find that I do actually know what they're talking about. I just don't realise that the word they're using is describing a certain theory. And I found, at least in my case, learning code on the job means I can write pretty good code, but this background knowledge, I'm sometimes none the wiser. The hows and the whys that I'm doing something a certain way, I don't know. I just know that that's the way to do it. So I'm going to try and break some of these topics down for you today. Quick disclaimer before we start. I'm by no means an expert in any of this. I'm just someone that finds this sort of stuff interesting and enjoys watching very random YouTube videos about technology and Googling lots of things. So yeah. So the topics we're going to look at today, there are literally hundreds and hundreds I could have chosen from, but we only have half an hour, and also I do not want to bore you to death with my ramblings. So I've just chosen a few of my favourites. So we're going to look at computers in general, programming paradigms, object-oriented programming, big O notation, and also concurrency. So, computers. As someone who spends a lot of their working day writing code, and also some of my free time writing code, I spend a lot of time telling computers what to do while having absolutely no idea how they actually work. So I did a little bit of digging, and according to the internet, the CPU and memory is kind of the brains of the whole operation. I mean, technically, a computer itself is a giant brain. But if we boil it down, the CPU and memory is the brains. So what are these? The CPU is the central processing unit. So this is basically made up of lots of tiny little microtransistors, which are essentially tiny on-off switches. So they can hold a value of either on or off, which is essentially binary. 1 is on, 0 is off. And this value is called 1 bit. 1 bit alone, super useless, so we put them together in groups of 8, which is called a byte. And then when we type programming code, it eventually gets converted into machine code, which is binary, which the CPU can then process and make things happen. So then RAM is also an important aspect. So this is random access memory. So this is like the physical memory of the computer, and it's where data is stored, especially for running applications. There are other types of memory, like the hard disk, where your files live and that sort of thing. But when it comes to programming, we care more about the RAM. So I was watching a YouTube video about this, and the guy on there said to think of RAM a bit like a neighborhood. So there's houses, and in each house lives a byte of data, so 8 bits. And each house has a memory address, and that's how we know where the bytes of data that we care about are stored. So there are two main bits of memory in the RAM that are important here. So it's called the call stack and the heap. So the call stack is short-term memory, and it's where our function calls and local variables get managed. So this operates on a last in, first out basis. So a bit like a stack of plates, you stack them up, the first one you use is the last one you put on top. So that's how the functions get managed. The last one into the call stack is the first one dealt with. And then we also have the heap, which is longer term memory. So this is much less organized than a stack. Instead of on top of each other, bits of information are kind of stored here, there, and everywhere. So here, memory gets requested and allocated as and when it's needed. So it's dynamic, which means it can grow and shrink, whereas the call stack is a fixed size. And it allows you to pass objects by reference, so by using their memory address instead of the actual bit of data itself. So that is essentially how computers work in a very quick 2-minute rundown. So our next topic is going to be programming paradigms. So these are the style of programming. So instead of the language, which cares more about syntax and naming conventions, that sort of thing, it's more about the way you program, so the design of the software, and provides us with a set of principles to follow. So there's two main types. The first one is imperative. So this is where your code provides quite explicit instructions on how to achieve something. And then these instructions are executed one by one until you get to your desired outcome. So this is quite command driven, so it cares a lot about control flow statements like if statements, while loops, for loops. Then the other type is declarative. So this more describes about what your program does and doesn't care so much about exactly how you implement it as long as you get to your desired outcome. So control flow is therefore not really seen as a priority because it doesn't matter exactly how it flows, just as long as you get to your outcome. So in a nutshell, declarative is what you want to do, and imperative is how you're going to do it. So I find an easy way to think about it is, say you've gone to IKEA, you've bought yourself a new coffee table. So you've got a bit of flat pack furniture. Declarative programming would just show you a picture of the coffee table. You can build that however you want. As long as you've got a good working coffee table at the end, it's all good. Whereas imperative, you're going to have step-by-step instructions that need to be executed in order to get your built coffee table. So you need to get part A to connect to part B, which connects to part C, and so on. So, although I've said there's two types, there's technically way more, but they both fit under the imperative or the declarative umbrella. So we're not going to go through each one of these today. We will look at object-oriented in a moment, but just a kind of awareness, there's loads, but it can kind of be boiled down to the two main types. So some languages belong to just one. So languages like Haskell tend to be a purely functional programming language, whereas most modern general purpose languages like Python, Swift, Koltin, JavaScript, all those kinds are multi-paradigms. They can fit under the umbrella of multiple paradigms. So one of the paradigms that I just mentioned was object-oriented programming. So this is where we organize software design around objects. So objects are chunks of data that live in the computer's memory. So they'd live in the heap and they'd have a memory address. Classes are super important in object-oriented programming, and these are the blueprints for these objects. So this is where an object's like attributes and methods can be defined. And in all honesty, a class on its own that has an instantiated object can be pretty useless, but once you instantiate an object from it, that's when the real magic starts to happen. So an example of a class, we have a class called car. And inside car, we have various methods like drive, get fuel defined, and attributes like fuel type, max speed, color, model, make, that sort of thing is all defined inside of car. And then we can instantiate some objects like Mini, Polo, Fiesta, which then use car as their blueprint and can then extend from there to define their exact object qualities. So in object-oriented programming, there are some main principles. These are especially the ones where at the beginning when I was saying people use all these big words and I don't always know what they mean, I tend to find I actually knew what these meant, but I didn't realize that these were the words to describe them. So The first one is abstraction. So this is when you're hiding the details of your code. So, oh, I've gone backwards. No, I've not, I've gone forwards. There it is. So this is in order to simplify complex systems, and in order to do this, you only want to show the absolute essential information. So you put the focus on what an object does rather than how they're doing it. So if we go back to our example of car, an object that has a car as its blueprint, like Mini or Polo, doesn't need to know exactly how the engine works, anything like that. They just need to know that you can call the method drive and it drives, but they don't need to know all the inner workings of that. So it just makes things a lot simpler. And then we've got encapsulation. So this is also about hiding information, but from more of a security standpoint. So this is through providing a public interface in which you can then interact with the object. So data can't be manipulated or accessed or changed without obvious intention. And in order to do this, we want to use access modifiers. So these can vary from language to language, but in general, these are our main three. So we've got private, which is the most restrictive. So this means only the class itself can access the state or information with a private modifier. Then we go down to protected. So this one's a little less restrictive. So this basically means that the class itself, a class inside the same package as that class, or a class outside the package that inherits from the class, can access the state and information. And then the least restrictive is public, which is basically a free-for-all. So anyone, anywhere can access the information with a public modifier. So with our car example, this is a very rundown version. So we've got a public variable called color and a private variable called fuel type, and then some public getter and setter methods. In this case, the public and the private variable plus the methods can all be accessed from within car. But if we're outside of car, we can't access the fuel type because it's a private variable. However, we have some public getter and setter methods, so we can go through these methods to access and modify the variable, but we can only do that through the methods, not directly to the variable itself. So this is why encapsulation is kind of a security layer in a way. So it's making sure that you have very obvious intention and it's kind of restricted to how you can get to private variables. And then our next kind of topic is inheritance. So this is where we're deriving a class from another class. So some keywords here, we've got subclass. So this is the child class, which is the class doing the inheriting, whereas a superclass or a parent class is the class being inherited from. So inheritance is a really good way that allows code to be reused and extended. So if we go back to our car example, car would be the superclass or parent class, and Mini, Polo, and Fiesta objects are our subclasses or child classes. They've inherited from the car class. And then polymorphism is our last kind of main topic around object-oriented programming. So this kind of builds on inheritance. So it allows an object to act as either its own class or its superclass or parent. So it uses inheritance to allow us to perform a single action in multiple ways. So to show you an example, if we go one up from car, we have a parent class called vehicle, and then car and motorbike are our child classes. So in code, it look a little bit like this. You don't need to fully understand this code, but basically we've got a class called vehicle that has some public variables called make and model, and a function called drive that returns a string, I'm driving a vehicle. So then we have a child class car, which inherits from vehicle, has its own variable called number of doors, inherits the make and model variables, and then overrides the function drive, which it's inherited. So it now returns, I'm driving a car instead of I'm driving a vehicle. And then motorbike also inherits from vehicle. So it has the make and model, it has its own variable called has sidecar, and overrides the function drive to return I'm driving a motorbike instead of I'm driving a vehicle. And also has its own function called wheelie that returns I'm doing a wheelie. So what polymorphism allows is we can instantiate some car and motorbike objects. So we've got a Ford Fiesta and a BMW X3, which are both cars. We've got a motorbike object called Yamaha R6. And because they can act as either their own class or their parent class, we can stick them all in an array of vehicles. Because vehicle is all of their parent classes, they can go in a vehicle array. We can then call the method drive on each of these vehicles, but because we've overridden the function drive in both car and motorbike, instead of returning 3 lots of I am a vehicle, it's returning I'm driving a car, I'm driving a car, and I'm driving a motorbike. So we've called the exact same function on all 3, but it's returned something slightly different. So that is basically polymorphism in a nutshell. So that was object-oriented programming. Okay. And then we've got big O notation next. So big O notation is essentially a simplified way of describing an algorithm's efficiency. So when we say algorithm here, it could literally just be a function, something that takes an input, does something, returns an output. And the O stands for order of complexity. So there's 2 types of complexity that we could talk about here, which is time complexity, which is how long it takes to run, and space complexity, which is how much memory is going to be needed for the algorithm to run. So complexity can change as the number of inputs can change. So inputs is known as n, and it's a way of abstracting the efficiency of our code from the machines that they run on. So it's not looking at whether you've got the latest high-tech machine or if you're running on a really old computer. It doesn't matter. It's looking at the efficiency of the code itself. So when I first Googled it, this is what was presented to me, and I had absolutely no idea what this graph was trying to tell me. I could tell lines that went quite upwards were bad because they were red, and the flatter the line seemed better because it was in the green section, but other than that, that meant absolutely nothing to me. So I found it a little bit easier to see it as a bit of a spectrum. So big O of 1, which is the flattest line in the green, is the most efficient. Big O of n factorial, which is the steepest line in the red, is the least efficient. And all the other versions of big O kind of fit somewhere in between the 2. I'm not going to bore you and go through what every single one of these mean, but we're going to just go through a few of the really common ones. So big O of 1, which is the most efficient one, is just a flat line, and it's called constant time. So this basically just means that the complexity is going to stay the same no matter how big n gets. So an example of that would be you have an array, this case 5 strings, which are just letters, and you want to access letter C, which you know is index 2. So that's going to take the exact same amount of time, whether it's just 5 strings in that array, whether you've got the entire alphabet of 26 letters, or it could be 1,000 items long. Accessing the item at index number 2 is going to take the exact same amount of time. So even as the array increases in size, locating values at a specific index will not take any longer, which is why it's called constant time and the most efficient. Then we've got linear complexity, which is big O of n. So you can tell by the line, way less efficient than big O of 1. So this is where it takes 1 unit at a time to loop over each element. So as your number of elements increases, your complexity increases. There's a one-to-one relationship between n and complexity. So an example of that, a simple for loop. As the number of items you're trying to loop through gets bigger and bigger and bigger, so does the complexity. And then we've got big O of log n, which is logarithmic complexity. So this, as you can tell, less steep than big O of n, but more steep than big O of 1, fits somewhere between the 2. So it scales well to a large number of inputs. An example of this is a binary search. So not going to lie, I didn't really know what a binary search was when I was doing this, so just in case you also don't. Say we've got an array of 10 numbers. We want to find number 7. We could just loop through them one at a time until we find number 7, but instead we could put them in order, take the middle number, in this case it's 2. Is 2 bigger than 7? No, we get rid of 2 and anything below it. That leaves us with 5 numbers. We find the middle number of this 5, which is 6. 6 is smaller than 7, so we get rid of 6 and anything below it. And then we're left with 2 numbers, so we take the first one, we found 7. It's taken us 3 iterations to find 7 in a group of 10 numbers, whereas if we were doing a basic for loop, it would take us 9 iterations. So 3 to 9 isn't a huge difference, but imagine there was 1,000 items in that array. They would take a lot longer with a basic for loop, which is big O of n, to do it, compared to a binary search, which is big O of log n. Hence, big O of log n scaling better to a large number of inputs. Okay, so why did I choose this topic? I think this one's quite an important one because I've heard people talk about the big O of their code, this, that, and the other, but I literally had no idea what it meant. But it's really good for understanding how efficient your code is and why. And it's very helpful when you want to design solutions to complex problems, when there's lots of different ways you could get to your desired outcome, but some might be more efficient than others. It's helpful to think of what the big O of each solution would be, because that could help you figure out the most efficient solution. And very, very important for scalability, as we'd see just with the binary search example. Doing a binary search rather than a for loop could make things run much quicker depending on your scenario. Cool, so then the last topic we're going to look at is concurrency and parallelism. If I say that word wrong, you know what I mean. So I didn't really know what the difference was between the two of these for a very long time, but concurrency is when different parts of a program can be run out of order or in partial order, and you still get your desired outcome. So I always thought this meant simultaneously, but something can be concurrent without being simultaneous. And as I said, I thought they were the same thing, but it's not parallelism, but it allows parallelism. So then parallelism is when you can run things simultaneously. So it's when a program leverages the hardware of multiple machines to execute separate tasks at the same time. So work gets broken up into tasks, and then each one gets executed on a separate core. A very common way of doing this is using threads, but there are other ways, but multi-threading is a common way of making things parallel. So a visual representation of that. So concurrency on a single core machine using one processing unit. You've got separate tasks. They look like they're all happening at the same time, but really one is running at each moment. Whereas parallelism, you've got multiple processing units, so each task can happen at the exact same time. So I appreciate I've thrown an awful lot of information at you in quite a short amount of time. So I'm just going to go through a bit of resource suggestions that I found has helped me learn a lot more of these things. The first one, I'm sure I don't need to tell you what YouTube is. I'm sure we all know what it is, but so good for so many great explanations on topics. A channel that I find really helpful is called Fireship. They do such good short explanations on topics, which I tend to watch first, and then I'll go from there and find something a bit more in depth. Coding challenges as well. These I found really interesting because you have to work out problems that you wouldn't get in your day-to-day. So things that I'm having to deal with in my day-to-day work as an SEiT doing automation, I don't tend to see in a coding challenge and vice versa. So you get to learn a lot of things, and often when you're trying to work something out, you end up having to Google something, which leads you to Google something else. You end up down a rabbit hole learning all sorts of different things. So Edibit, LeetCode, and Coding Game are three of the ones I tend to use, and they're all very good, so I would recommend. And then also personal projects. So I'm currently in the iOS team at SkyBet, and in that I'm writing Swift, so I've been learning how to do some iOS apps. So in my free time in L&D, I've been working on various different apps, which again, you get to learn things that you wouldn't learn in your day-to-day. So the first one I did was an iOS version of Wordle, which I literally just watched some lovely man named Stuart on YouTube talk me through step-by-step what I needed to do. I then took the learnings from that and made a numbers version, which is slightly different, but used the basic components that I learned how to make in the Wordle. And then I've also been working on a mountains app, because I like going and climbing things, where you can find out information about mountains in the UK, and I want to add the ability to like log climbs and things like that. And these are just for fun. None of these are on the App Store, but maybe one day. But yeah, so it's just doing something that you want to do for fun is a really good way of learning. And things that I've learned through doing these apps, I can apply to my automation. So even though they're not testing specific, I still can learn to put towards my work. But yeah, so that's it. As I say, I appreciate I've thrown a lot of information, but thank you for listening. And if we have time, if anyone has a question, feel free to shout it at me. If not, find me at some point today. But yeah, thank you.